Hello viewers of AraaTech. Once again presenting a new topic, convolutional neural networks, CNNS, and artificial intelligence. Let's start our topic. CNNS or convolutional neural networks are a class of deep neural networks primarily used for image recognition and processing tasks. How it works with artificial intelligence. Inspiration from animal visual cortex. The structure of convolutional neural networks draws inspiration from the organization of neurons in the visual cortex of animals, particularly in mammals like cats and monkeys. In the visual cortex, neurons are organized in a hierarchical manner with lower level neurons responding to simple features like edges and corners, while higher level neurons integrate information from lower levels to recognize more complex patterns like objects or faces. Multiple layers of neurons. CNNS consist of multiple layers, typically including convolutional layers, activation layers, pooling layers, and fully connected layers. Each layer is composed of neurons, also known as units or nodes, which perform computations on the input data, processing portions of input image. Convolutional layers in CNNS process portions of the input image known as receptive fields using convolutional filters or kernels. These filters are small matrices that slide over the input image, performing element-wise multiplication and summing up the results to produce feature maps. By applying different filters, the network can learn to detect various patterns and features present in the input images. Convolution, activation, pooling, and fully connected layers. Convolution. This operation involves applying the convolutional filters to the input image to extract features. Each filter captures a specific pattern or feature. Non-linear activation. After convolution, activation functions like ReLU, rectified linear unit, introduce non-linearity into the network, allowing it to learn complex relationships between features. Pooling. Pooling layers reduce the spatial dimensions of the feature maps while retaining important information. Max pooling, for example, select the maximum value within each pooling region. Fully connected layers. After several convolutional and pooling layers, the feature maps are flattened into a vector and passed through one or more fully connected layers, which perform classification or regression tasks based on the learned features, learning to recognize patterns and features. Through the iterative process of forward and backward propagation during training, CNNS adjust their parameters, weights, and biases to minimize the difference between predicted and actual labels. By learning from labeled training data, CNNS can recognize and generalize patterns and features present in images, enabling tasks like image classification, object detection, and facial recognition. Overall, CNNS leverage the principles of convolutional nonlinear activation, pooling, and fully connected layers to efficiently learn and extract hierarchical representations of features from input images, making them powerful tools for various computer vision tasks. Role. Defining architecture. The architecture of a CNNS refers to its overall structure, including the arrangement and configuration of layers. This involves decisions such as the number of convolutional layers, the size and number of filters in each layer, the type of activation functions, that is ReLU, sigmoid, and TANH, the use of pooling layers and the number of fully connected layers. Architectural choice often depend on the specific task and the complexity of the data. Hyperparameters. Hyperparameters are parameters that are set before the training process begins and remain constant during training. Examples include learning rate, batch size, dropout rate, a regularization technique, padding size in convolutional layers, and stride size, the step size of the filter during convolution. Tuning these hyperparameters is crucial for achieving optimal performance and preventing issues like overfitting or underfitting. Data pre-processing. Before training a CNN, it's essential to pre-process the input data. Common pre-processing steps include resizing images to a uniform size, normalizing pixel values, scaling them to a range like 0, 1 or -1, 1, and augmenting the data, creating variations of the original images to increase the diversity of the training set. Training process. Training a CNN involves iteratively presenting batches of labeled images to the network and updating its parameters to minimize the loss function, which measures the difference between predicted and actual labels. Optimization algorithms like stochastic gradient descent (SGD) or its variants, that is ADAM, RMSPROP, are used to update the network's weights and biases. Backpropagation, a technique for calculating the gradients of the loss function with respect to the network's parameters, is employed to propagate error signals backward through the network. Evaluation and fine-tuning. After training, the performance of the CNN is evaluated using a separate validation set or through cross-validation techniques. If the performance is unsatisfactory, the hyperparameters or even the network architecture may be adjusted and the training process may be repeated. Fine-tuning. Transfer learning, where a pre-trained CNN is adapted to a new task with a smaller dataset, is also a common strategy, especially when limited labels data is available. Deployment. Once trained and evaluated, the CNN can be deployed for inference on new unseen data. Deployment may involve integrating the CNN into large systems or applications, optimizing its performance for real-time or resource-constrained environments, and ensuring robustness to variations in input data. By carefully designing the architecture, selecting appropriate hyperparameters, pre-processing the data, and training effectively, CNNs can be implemented to solve a wide range of computer vision tasks with high accuracy and efficiency. Characteristics. Feature learning. CNNs automatically learn features from the input images, reducing the need for manual feature extraction. Translation invariance. CNNs can recognize patterns regardless of their position in the image, making them robust to translations. Hierarchical representation. CNNs learn hierarchical representations of features, starting from simple edges and shapes to more complex objects. Scalability. CNNs can scale to process large datasets efficiently thanks to parallel processing on GPUs or specialized hardware. Adaptability. They can be fine-tuned for specific tasks using transfer learning, where pre-trained models are adjusted to perform new tasks with less training data. Positive aspects. High accuracy. CNNs achieve state-of-the-art performance in many computer vision tasks. Versatility. They can be adapted to various tasks with appropriate adjustments to their architecture and training. Automation. CNNs automate the process of feature extraction, reducing the need for manual intervention in tasks like image analysis. Real-world applications. CNNs power numerous applications that impact our daily lives, from image recognition on social media platforms to media diagnosis systems. Negative aspects. Data hunger. CNNs require large amounts of labeled data for training, which can be expensive and time consuming to acquire. Computational cost. Training CNNs, especially deep architectures, can be computationally intensive and require powerful hardware resources. Interpretability. Understanding why CNNs make certain predictions can be challenging due to their complex architectures, leading to issues with transparency and trust in some applications. Vulnerability to adversarial attacks. CNNs can be flooded by carefully crafted input data, leading to incorrect predictions, which is a concern in security-sensitive applications. Overall, CNNs are a cornerstone of modern artificial intelligence, particularly in the field of computer vision, with numerous applications and both positive and negative aspects to consider in their implementation.